I think we are past the waiting time. So, okay, so first I will start with the format that how I am going to go through this presentation. So, I'll start through coroutines, basic and few basic things of which we need. Those are prerequisites for this presentation, and then I will move on to why we are doing this, why we are discussing about coroutines. Where was it earlier? I mean, why we were waiting for so many days to discuss about this? Why aren't we using it till now? And then I will do some code walkthrough, which I mean some code snippets, single function or single class, and that I will explain to you and what I'm trying to achieve there. After the coding part, I will explain that the what are the real world scenarios where we are using this, and who are using this, which language, which library or which package are using this concept of coroutines for their purpose. And then after that, we will go into the question round that you will ask some question, or in meanwhile also you can ask in chat. I'll go through those questions and I'll try to answer my best. Also, one more thing is that while code walkthrough, it might happen that because I am not like a very good, I can't write code faster, so it might be a little bit slow for you. So bear me with that. And yeah, so that will be the format of this. And yeah, so okay, so I think we are good to go. We can start, right? Okay, cool. So if we start with the slide that I mean why coroutines, right? What are the basic fundas? What it does. So there are two terms. One is concurrency. Another thing is parallelism. So first we need to know the difference between concurrency and parallelism. Parallelism brings a multi-processing kind of thing where you have multiple workers doing the same task to quickly wrap up those things or make it more robust and make it more faster. And so multiple workers are doing their job onto one task, splitting it up into different parts, and then making it faster. So that is a way to scale by doing multiprocessing. Another way is concurrency. Concurrent means you need to release the CPU for all your blocking calls. So blocking calls might be the CPU. I mean, sorry, IO, or it might be something else, some blocking calls basically. So in that case, I will also be sharing one more um, a whiteboard basically where I need to explain. I mean, I can't just write everything down in slide, so I need to use that also. So I might be using that also. So this will be my whiteboard, and yeah. So this will be my whiteboard. So here I will be drawing some stuff. So I try to explain to you what I'm talking about. So yeah. So if there's one task and so there's one task which we need to execute, and there are suppose two workers. So they will split the task and they will do their own bit, and that's how it will do for parallelism. That these workers will work in parallelly. Now again, if we go into the concurrency part, then it will be more like of so there's one job which is running, and suddenly it calls for IO, and so at that point the CPU got released. Sorry, yeah. So at that point CPU is released and it's available for other workers to pick up. So suppose if this task is suppose T1, and so from here the CPU will pick another task, which is T2. Now I'll explain more about how again CPU will regain the access of this task in its execution. So how this will get scheduled again. So this I will explain later. And so this is kind of a, I mean, it's a little bit tricky that how they manage this, and you can say it's kind of a limitation also for coroutines. And yeah, so the more you might have heard of GIL, global interpreter log of Python. It's a very infamous issue of Python which they decided, I don't know why, but that's the, yeah, that's their decision, that's how they went, and now it's a problem for everyone. So what it does is it doesn't allows you to do multi-threading using Python, because it doesn't handles its threads on its own. It passes to OS threads, and GIL is the kind of global interpreter log. So whenever the interpreter is on, it has a global log. So you can't do multi-threading natively in Python. So what you can do is multi-processing. You can have multiple processes. So for that you need multi-core CPUs, right? So that's the limitation of Python, and because of that, threads are not supported natively. Again, you can say JavaScript is also kind of have the same problem. It's single threaded, and and hence they used callback. If you guys know, the callback stack is there. So basically, if one function is sorry, yeah, if one function is if one program is there, P1, which is running in JavaScript, so what it will do, it will maintain a call stack, and it so all the async calls, it will go into this call stack, and whenever it does execute, it returns it back to this. So that's how the callback and all works in JavaScript. So sorry, yeah, so that's how it works in JavaScript. So and I think that's a very neat way to handle this single threading problem. And I must say that yeah, I mean you handle it, but it's not the only good way to handle, right? I mean there might be different ways to handle this. One of those ways is coroutines. So yeah, and we know that multi-threading is good. I mean, yeah, I mean we should do multi-threading. We have we have good optimization on multi-threadings, and it's a good way to scale. I mean, you can have multi-threading option also, but the problem with multi-threading is that, so suppose this is one program P1, which is like which is thread 1 is running here, so thread 2 should run here. So as you can see, these are kind of program copies. So this has like different memory allocation, different call stack and all, and also there's a limit to this, right? I mean, it depends on what's your RAM size. In case of Linux, in case of Mac, you can have maximum, I guess, 2000. I'm not sure. You guys can verify. So 2000 threads max in Mac OS. So there are a few limitations basically, and you can't have multi-threading every time. So you can have like multi-processing, but again, it's making your context switch very very heavy, and the copies of your context data will be there. So yeah, so that problem is there. So multi-threading and multi-processings are good, but with their own disadvantages. Yeah, so Python's infamous. So how to start this is basically we will go into the code. So few things, as I said, yeah, few things I will explain via code. Yeah. So the code, I guess, is visible, or shall I? It's visible, right? Okay, guys are complaining about Twitch. Yes, yeah, they did the workaround for multi-threading in JavaScript. See, multi-threading is also, I mean, you can do multi-threading in Python also. That's but it's again, it's not native as it is with Java, you might say. So yeah, so that's the thing, and okay, so yeah, first thing we need to know is what are generators. First thing. So this is a sample code which I took. Yeah, which I so this is a very sample code of generating random integers. So you might see if I do something like this. This is an iterator, right? So we all know that we need to if we want to iterate on something, we need a iterator, and for now we don't need this. So there's a method called nextgen, and sorry, the next method. What it will do is, I'm not sure whether it will run or not. Yeah, fine. So I have to call the main method. It's positional argument. So we need to specify how many random integers we want, and we need to print this. Yeah. So you can see if I print next, it will return one. That is the first value from the iterator. But what if I do a for loop basically for I in gen print I. So what this for loop does it automatically calls the next method of the iterator, and it will keep on calling until the iterator the stop iteration comes. So there's a call stop iteration in Python which invokes when a iterator ends. So when there are no more numbers or no more elements in the iterator. So this is how it's working. It's dead simple. We are taking an array, we are appending it to it until and unless, and then we are returning that iterator. Okay, so as you can see, we are storing the all the numbers in array. So it's basically you are putting all your elements into a memory before using it. So yeah, so that this is not good. I mean, if you are trying for a very large number of random numbers, if you want like 10k or so this is not a good approach to load everything at once in your memory. So yeah, so a workaround of this is using generator. So what it does, it basically yields. So there's a statement called yield, which will. So if I run this in suppose in a debugger, then I guess it will be more easy to visualize. So I have to make yeah. So I'm putting a stop at a breakpoint at yield, and yeah. So if you say see it stopped at yield, and if I do next, it will print 11, and again it stops at yield. So what is happening here? If I So what's actually happening here is basically you are kind of sending the call, or the if you think of it as a event loop, and in that loop you need to pass your function, and you want to pass the relay. So you are passing it to the generator function, and again you are kind of making it again back to uh, the main function, the calling function. So suppose this is the main function and this is a generator function. So basically, whenever you are calling next here, it's actually invoking and making a call to the generator function. It's returning a value, it's printing it, and then again when next getting called, it's again calling the same generator function. So it's not like you are having everything in your memory at once, and yeah. So that's a good thing, right? Okay. So if I continue, yeah, it prints everything. Pardon the parse git branch. It's something I did with the terminal. So yeah. So this is the generator. So but how, when this yield is getting invoked, when we are reaching this is getting invoked when we are calling the next. So if I do a print gen here, so we can see that what's inside. I mean, what the generator function returns in this case. It returns a generator object. But if we go to the iterator one, if we call the iterator function, it's returning the iterator object. So for now I'm moving out of the iterator. Yeah, with the generator object, if we call next, so if we call print of next gen, yeah, so that is actually invoking the yield statement basically. So this is what generator is. But again, see, I'm trying to make you familiar with yield statement, but generators and yield is not only to replace the iterator. So we are going to explore this yield part again and again in this presentation. So this is very important. I mean, this yield is very important. Yeah. So okay. So if I explain the generator more of kind of in a very basic term, so it will be kind of uh, it's a object which has its own frame, and its own attributes, local variables, and all. So if you guys can remember the C pointers, so you can say that it kind of the pointer is going back and through from generator function to the calling function. So it's kind of like that. Okay, I think you guys are facing some problem. Is it working now? Can you see my changes? Okay, cool. Yeah, so as I was saying, so if you what if we can, if it has a separate frame, if it has a separate attributes, can we send something to the generator? So right now we are just consuming, we are yielding from there, but can we send also? So it will be kind of a suspend and resume thing. We are suspending the main function, then again we are resuming when we are getting the pointer back from the generator function. So let's try about how to send. I think I have some code. Let's try this one. And okay, I need to save. Sorry. Sorry guys, I don't know. Okay. Are you guys able to see my screen? Okay. I should ask the first question first. Are you guys, am I audible? I think some issue. Okay, cool. Okay, cool. So, yeah. So what if we want to send something to this generate random function? So in this case, what I'm doing is I'm not initiating anything uh, while uh, uh, while initiating the function. I'm not passing anything. What I will do, I will use the send method for passing some value, and then I will try to print it out. So let's see. I don't know why I need so many bash. Okay. So as you can see, I passed. So the first print, I should get rid of that. Yeah. So you can see I passed 4, and it went there. It came to yield, and then it just prints the number I just passed. And again, I mean, sorry. And then it called the stop iteration exception. So what if I don't do next and just I do the send? You can see that can't send non-none value to a just started generator. So what this basically means is when you are initiating the generator, that doesn't mean that it's going to invoke. So you need to either call next, or you need to send none. So if you do this, then after this only you can actually invoke this statement. So this is kind of a trick, and also to avoid the stop iteration thing, you should put it in try except. So you should handle this exception, and you should just I will just print out a friendly message to end. Yeah. Okay. So yeah. So if I do send none, then it will work. And after that, if I do send five, yeah, that will work, right? Okay. So I guess send is clear, right? Till now we are okay with generators and how everything is getting along. Any doubt or any question till now? See, after this, I'm going for uh, for coroutines, event loop, and all the stuffs basically. So if till now everything is clear, then we can go ahead. Okay, no doubts. Cool. Probably I'm explaining in a very awesome way. Okay. Uh, no issue. I mean, you can ask your doubts later also. You don't have to just ask. I mean, I will go through the chats later also. So, but after this, things are going to be little serious. So, yeah. If anyone doesn't have any familiarity with Python syntax, then I guess they can ask that also, that why this or what this. So that is also not an issue. Okay. So now we will go to the core routines and let me see what will happen with the one function which we didn't explore. So what will happen in this case if I just call the countdown method. So so can you, I mean, can you guess what's going to happen here? What are the guesses? I mean, because see, we are using the same yield thing here. We are assigning it to a value n, and then if it's a new value, we will just go down and drill down, and we will just I mean, there's nothing magical here, right? We will just, it will just count down to till the end. That means if I call countdown with 5, it will do countdown till 0, right? That's very basic thing. And what if I do something like this? So yeah, what if my main method is this, and for now I am commenting this. So what if my main method is this? What will happen then? The guy with no doubts can answer, I guess. So just to make it more, I mean, putting this same. Yeah, awesome. So it will start from 5, then it will jump to 3, and then yes, it will go till 0. So that's how it's equal to 0, so it will go till 0. So yeah, so congrats, but there are no prices. Yeah, and so yeah, moving on. So this is very important concept that you need to understand how, in this case, this generator is actually producing and consuming both, right? So it's also producing the values, it's also consuming the values, so at the same time. So this is very important example to go through, because it will help us in coding. Yeah. So you might have saw this thing, a main method which I deleted. So here we are doing try except stop iteration kind of thing. So we need to do this whenever we are dealing with coroutines. So we can have a nice decorator. If you guys are familiar with decorator, it's nothing to be nothing related to this presentation. Just to tell you that you can have this. You need to call next or send every time, so that thing can be kind of handled with this decorator. If you use this decorator of any function, you don't need to call this send manually. So if I do something like this, uh, if I put it here, sorry, here, and if I just decorate this function with coroutines, I think we will not need to be calling the send none as we were calling earlier. So yeah, so yeah, so we don't need to call send none, because it's already calling the next on it, and that's how, I mean, it's a kind of syntactic sugar, nothing else, nothing to stare at it. It's pretty simple. Okay, so moving on. Now going to the definition of coroutine. So what we saw in the countdown is basically a coroutine. It's the same concept. So if we go back to if we go back to the OS, OS concepts basically. So we can see that there's something called scheduler, right? And scheduler, what it does basically, it schedules things. I mean, not exactly that, but yeah. So in OS we saw that there are multiple types of scheduling, right? There it might be something called preemptive. You might have heard. I'm not sure about the junior guys, but you might have heard of preemptive scheduling, non-preemptive scheduling, and all. So those things are there in OS, right? So if we go into those concepts, if we go through that, so there's something called, you might have heard of uh, yeah, you might have heard of changing the context. So some program is running, and this is our CPU, suppose, and some program came to do his job P1, and one thread is doing this job, and some IO call happened, and this is the IO part. It went for IO, it waits for IO, it send back here, it continues, and it finishes. Right? That's the simple uh, life cycle. I'm not going into suspended IO, suspended wait, and all those kinds of things. It's a simple life cycle basically. So what will happen if this process takes too much time or too much time to CPU? What will happen? I mean, there will be list of programs, right? We are not just our system is not prepared for only one program at a time. We have multiple programs running. So what will happen if one program is taking all the CPU usage for a particular time, which is very large? So in that case, what will happen? So I think yeah. So I think if this P1 is going to take too much time, then this queue will get stacked up, and nothing will get popped, and that will increase that will cause a kind of a very extensive use of CPU, which is not correct for any program. So what scheduler does is it 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 removes this P1. It says that go for some time in suspended state, and we will resume after we do some processing of a different program. So this is the way. I mean, sorry, can't see CPU. Okay, I guess now it's visible, right? Yeah. So so it will send the P1 to suspended state. It will carry another program P2, and then it will again resume it when it's done with P2, or if it sends P2 to another to again to the suspended state. So basically there are multiple queues. There are multiple queues to have a definite state, and to maintain these things. The, there are different things, right? So what are the possibilities? It might be that there must be something called ready queue, right? You might have heard of. There must be something called waiting queue. I'm pretty sure it's not called waiting queue. It's suspended queue, but for the sake of simplicity, some waiting queue, right? Some ready queue, and just for the sake of our understanding, something called uh, done. This is kind of completed queue, you might say. So all this queue will have all the programs, and according to their state, it will be in the queues, right? So what coroutine does different? It's not actually different. The difference is just on a single thread. That's all. A single thread is running, and in this thread, there might be different coroutines. So what advantage it gets is it's basically the context switching is not happening, right? Again, the map, the copies of context variable is not in all the places. So memory is kind of, we are saving the memories. So these advantages we get, and also the number of coroutines can be it depends on your processor and RAM usage. So that also we are, it's actually pretty, I mean, if you compare number of threads and number of coroutines, it's actually 1000 or times more. So that level of scalability we get from coroutines. So of course, if this is happening here, then it also must have something called suspended, something called resume, right? So what we did here, let's see. So if you see the generator method, so you can see that we kind of suspended the main function when we called send, until and unless we are actually returning from this generator function, and then again resuming the main function. So that was kind. So this is something we can say that it's a coroutine. So this is the simple. This is the basic concept on which everything is built upon for scalability in Gevent and other libraries you see. So uh, yeah. So this is the basic simple example. You need to suspend your main function. Then again you need to resume your main function. So if I think of a use case out of this, I wrote a scheduler basically, a kind of mimicking the OS scheduler here. So I will just walk you through from this code quickly. So this is basically a simple object of task. It will have a task ID, and it will have a target, some value, and yeah. So and it will have a method called run. This is the main scheduler which will schedule the task, and also for the sake of now, I think yield will work. We will go into async await later. Yeah. So yeah, for now we will go with this. Yeah, and if you can see, scheduler has few methods, and one is new, which will generate a task. One is schedule. This is the main loop. And main loop, you can think of it as a, so I don't know if you guys are familiar with event driven programming. So event driven programming is basically, if I explain it to you, I think I need my uh, sorry, the screen is going to be a little bit haphazard because of so many tabs. Yeah. So if you see my whiteboard, then yeah. So you can think of it as a, mm, yeah. So you can think of it as a, so suppose there's a while loop, right? So in this while loop, suppose this is a single while loop thread which is running continuously, and it's going to run continuously, right? What it will do, it will poll and it will check that whether there are any events coming or not, and if some events comes, what action needs to be taken. This is a simple example of event flow. So it kind of it kind of it kind of says that, okay, when a event A will occur, kindly do B, kind of thing, and it will run continuously. It's a forever loop kind of thing. So yeah. uh, Okay, coming back to the scheduler code. So I will first run this code, and if you guys can see what's happening, we will explain more about this. Okay, I'm not sure why I imported async IO. Am I using Q? Yeah. Okay. So it kind of basically scheduling my task, the two tasks, foo and bar. So you can see once it's getting scheduled foo, one then again bar, then foo bar. So kind of like that. So it's basically uh, it kind of switching between two coroutines, you can say. So it's kind of mimicking thread, if you guys can see that thread switch kinds of happen like this only. But with this is how coroutine works. So this is a simple scheduler. It schedules new tasks. It puts it into the task queue, and it takes until and unless the task map is empty. It takes the task, it runs it, and then again it's schedule the task into the task queue. So it's kind of that's why it's not getting emptied easily. So if I also add something, I'm not sure. Suppose I am removing this. I think I need to add one more thing. Yeah. So you can see that my main loop is still running, but since I didn't schedule again, my tasks are not going into the task map, and that's why it's not going to, sorry, the task queue, and that's why this get is returning empty. So there's nothing to run here. That's why it stopped. I think my laptop is crashed. Yeah. Uh, basic basic laptop problems, I guess. Okay. So yeah. So moving on with the code again. I need to open VS Code. Yeah. So so next the second point, that is how we reached here. I mean why we are doing this, right? So there's something called some guy put a some delegation or some recommendation to pep 380. If you guys can go and check, the code is pep 380. You can go to the abstract, and why they put yield from, and then from yield from we are now at everything. So you guys can go and check how it started. And the current scenario is basically Python 3 has its awesome async IO library. You can do async await, async def, and so basically async await is kind of replaced with sorry, yield from is basically replaced with async async sorry, await. So those you can. I will share the current scenario. So yeah. So if you want to write some code with async this. Yeah. So yeah, with I'm trying to print numbers from till 5. So basically, what I'm doing here is I'm telling the so await async nothing. It's similar to yield. What it does, you can generators. So if I have something to yield, you are calling sub generator from your main generator. So in this case, you are calling subroutine from your main routine. So it's kind of like that. And again, you can see that what. So if you guys remember that, sorry, I think you guys missed the async IO part. So this is the code, and yeah. So here you can see that there's something called await. You can replace this from yield from. So yield from is nothing. It needs to it's kind of a sub generator calling. So you are calling a sub generator from subroutine from main routine, kind of like that. So kind of like this. So await is nothing fancy. It replaced with this. So yeah, moving on to I'm adding my one more string. Okay. Yeah. So if you guys can see, uh, yeah. So that's how the routine works. That's how everything. I mean everything around coroutine, and you can have multiple use cases. But I think you guys are thinking about. I mean, yeah, it's a very good concept to have. But what about the main use cases? Like, I mean, where are we using this? So if you see G event,